Welcome everyone to a new video. In the previous video, we learned how to develop the recession limb of a hydrograph. In this video, we're going to keep learning about hydrographs and how to work with them. To learn more, we're going to solve 4 problems. The first of them is 6.26. This problem says, consider the following runoff hydrograph. If the watershed area is 100 acres, what is the rainfall excess expressed in inches under the runoff hydrograph? This is the data given. They give us the time intervals and the runoff at each time interval. A way to understand this, if it's still not clear to you, is how we measure the rate of water crossing a gauge station at certain time. At the first hour, this is the rate of water passing that gauge. Considering it's being constant, right, during their specific hours. To understand visually more what's going on, I plotted these values, and all I have here is the time in hours on the x-axis and the runoff on the y-axis, and they are asking us for the rainfall excess, which in other words is like the volume of all that water. So whatever didn't infiltrate into the ground and is running off, this is all the water, but in the rate. To calculate the volume, we need to find the area underneath the curve. And all we need to do is pretty much to find any volume in here, you just need to multiply the runoff in cubic feet per second times the time. You gotta make sure it's in seconds always, also. So seconds cancel and you just are left with cubic feet. And that's what we're going to do pretty much to solve this problem here. So we have a cubic feet per second, which is runoff rate. Extend this runoff rate. So we're interested on the rainfall excess volume. So let's convert this cubic feet per second to cubic feet. To do that, let's do runoff, and this is gonna be only cubic feet. All we need to do is multiply this. To get rid of the seconds, we need to multiply by how many seconds there are in an hour, which is 3600. And now all these values is like the amount of water in cubic feet that has crossed that gauge, that's passed that gauge. And let's convert, we have it in cubic feet, so let's get it into just inches. And to get it into inches, let's do runoff. To make a runoff depth only in inches, let's do the conversion. Let's first divide it by the area, and we're gonna get feet. Cubic feet by the area. We're gonna have feet, but the area for us is given in acres, so we need to convert those acres to feet. And also, we're gonna have 1 foot left, so we need to convert that foot into inches. Hopefully, you can do that manually and you understand what I'm trying to say. I don't wanna lose much time on that, but this is just a simple conversion that we've been doing throughout all these videos. So we grab the cubic feet and divide it by 100, which would be 100 acres is the area. So we have cubic feet at the top, acres at the bottom. Now to get rid of the converted acres to feet, we have in 1 acre, we have 43,560 square feet. And then we need to multiply now to get rid of the feet and convert it into inches. Now we have in 12 inches over 1 foot. And this should gives us, hopefully this is working now. And now we have the runoff depth per each hour. And let's sum up this equals to the sum of all of this, right? The sum of each one of them will give you the total depth volume. So what we have found here, this is in inches. And this is what they're asking us for, the rainfall excess expressed in inches under the runoff hydrograph. All we have found is the volume that this hydrograph, volume of water that this hydrograph represents in inches. So this is the answer for this first problem. Let's get rid of some of the decimals because we're gonna need this value for the next problem. The next problem says, develop a unique hydrograph for problem 626. Also plot the results. So what we're doing here pretty much is solving, uh, learning how to develop a unique hydrograph. And remember, in the first problem, we got runoff values, and we're going from the runoff values, using these runoff values to develop a unique hydrograph to represent this watershed of 100 acres with these given values of runoff. So first, we need to find the volume in inches uh, of that storm, and we have done that, 5.8687 inches. Now, to develop the unit hydrograph, the unit hydrograph all it means is that it's a plot of runoff flows where the volume underneath is 1 inch. So all the values of runoff represent a total volume of 1 inch. It's not dividing it or multiplying by 1 inch, it's just a comparison. It's saying this plot represents 1 inch of volume. Since it is a comparison, all we need to do here to find the unique hydrograph in CFS is dividing each of the flows by 5.87, which is the precipitation depth, sorry, the runoff depth that we found in the previous problem. And if we do so, we get all these values. Let's get rid of some decimals. We find all these values. And now, if we plot these values, let's do so. All those new values that I found are the flows that will represent 1 inch of runoff volume. And we're also asked to plot them. So let's do that. Let's grab all our data. Let's just insert chart. Make sure you're using the smooth. And in the x-axis, we want our time, which is in column. What is that? C? I guess it's any of these ones, huh? This is the x-axis. Let's remove, and then we want to plot the column E and F. So let's remove this one, and here we go. So this is the hydrograph that represents 5.87 inches of runoff volume, which is this column. And this in red is the hydrograph, the unit hydrograph, because it represents the same storm, but with now these flow units of runoff. So if we were given, let's say, why do we do this? Let's say we have that this unit hydrograph represent that watershed of 800 acres on a for a storm like that. Let's say that we have another storm that happens in the same location, but this storm only had 3 inches instead of 5.87 inches of runoff volume. All you need to do, because you have the unit hydrograph, you multiply 3 inches by each single value here. 3 inches times 0, 3 inches times 11.93, and then you can plot what it will be the unit hydrograph of that area, since you already have it's like the unit hydrograph is like a template. I think there is no easier way to explain. It's a template of how water runs off on that watershed. So it's very useful. If you don't have all the area, you just need to know the amount of water that ran off, and then you multiply by the template, or in other words, the unit hydrograph, and you'll get the plot for that storm. Obviously, it's not easy to know. No, obviously, I shouldn't use that word because sometimes things are not obvious, but it's really hard to know the amount of runoff volume. So let's say if it was 3 inches, we just multiply it, but how do you know it was actually 3 inches? That's really hard. But for the purpose of this video, usually we are given those rainfall excess, the amount of rainfall volume. So this is all you need to do here. Just divide all of this by the 5.87 and you'll get the unit hydrograph. And before I move on, I want to clarify that we are not like doing 70 CFS divided by 5.87 inches. We're not like dividing CFS by inches. It's just a relationship. It's like saying, let me use, if let's say I make $5 an hour, and if I work 2 hours, then I'll make $10. So there is a relationship of how much money I make per hours I work. In this case, there is a relationship of how many cubic feet per second there are, depending on the rainfall excess volume. If it's 1 inch, 2 inch, 3 inches. If it's 1 inch, it's 11.93 at the first hour. If it is 2 inches of precipitation, it's gonna be 22, almost 24 inches at the first hour, and so on. You just multiply it. It's just a relationship. It's not an actual calculation of CFS over inches. Hopefully it is clear what we're doing here. Problem 6.28. What size in acres of watershed produce the following unit hydrograph? Now this is runoff, but this is a unit hydrograph. Uh, the flow rates are average hourly data. What is the precipitation volume if the runoff coefficient was 0.5? Okay, let's go one by one. What is the size? We know the size of the watershed or the the area. The area equals volume divided by the depth, right? The volume depth. Um, how can I say that? Yeah, just say depth. um, so we have that equation, right? That's how we've been finding the area. Now, the volume, we need to calculate it. We have the cubic feet per second. So let's compare just to cubic feet, and pay attention that each interval is per hour. So all you need to do is again multiply that by 3600 to get rid of the seconds. And now you just have the volume in cubic feet. Um, with this information, you can just sum it up, all of them. And this is cubic feet. Cubic feet of water is 720,000 cubic feet of water that we got on this storm of 6 hours. Now that we have the volume, all we need to do is divide it by the depth, but we know it's a unit hydrograph. So the unit hydrograph is gonna be 1 inch. So you have at the top area equals, and you have the volume in cubic feet divided, let's just equal this value divided by 1 inch. And right now we have cubic feet per inch, and we are given the area. So sorry, we need to find the area. So right now we have to convert this cubic feet to acres. So we know, let's do this. This is cubic feet. Let's do it again. This is inches. Now to get rid of the cubic feet, let's convert it into acres. 1 acre is equal to 43,560 square feet. And then we get rid of the inches. So in 12 inches, I'm not doing this right. This is 1 acre. This is square feet. And then to get rid of the inches, we got 12 inches and 1 foot. So we have cubic feet at the top, square feet and feet. Those cubic feet cancel, and then these inches cancel, and we got left with the acres. So if we solve for that, let's do this. This is equal to equals to this times 1 times 12 divided by 1 times 43,560 and times 1, right? And that gives us acres. Oh, I think I get it. There we go. So we got 198.35 acres, and that's the area. That's how we find the area with a given runoff. Unit hydrograph runoff. Now they ask us to find the precipitation volume if the runoff coefficient was 0.5. If you remember the equation, that the runoff equals the amount of precipitation times a coefficient times a runoff coefficient. So C times the precipitation. And they are asking us for the precipitation. So precipitation is going to equal runoff divided by C. So the precipitation is going to be equal to the runoff divided by C. And we know that the runoff volume is 720,000 cubic feet. And we have to divide it by the coefficient, which is 0.5. But before we do that, let's convert the runoff um, into inches, which since this is a unit hydrograph and this is its volume, we know that this cubic feet in inches is going to be just 1 inch because the unit hydrograph by definition has 1 inch of runoff volume. So all you need to do here is use the runoff volume, which is 1 inch divided by the runoff coefficient of 0.5. Oh, I forgot the equals. So you get that you have a precipitation of 2 inches. And that makes sense because again, this is a unit hydrograph. So the volume needs to be 1 inch. The runoff volume needs to be 1 inch. So that means that if the runoff coefficient is 0.5, well, that means that the precipitation must have been double that, right? So this is the answer for the second question, 2 inches. Now let's move on to the last problem of this video. And we're gonna work with unit hydrographs. And we are given data for a specific storm, but this storm had 3 different rainfall excess periods. Let's read the um, the problem. 6.29. Given the unit runoff hydrograph of problem 28, the previous one that we just did, develop a composite runoff hydrograph given the following rainfall excess values. Set up the problem and complete with all three methods: convolution equation, matrix multiplication, and table methods. So what's happening here? Usually we've been working with a hydrograph. Where do I have? Here. This one. Let's use this one. Here we just assume that there is one. This storm started, continued, and ended in all in one shot. But usually that's not the case. When rainfall happens, usually it rains a little bit. Sometimes it stops for 5 minutes and then it starts again, and then it stops and then it starts again, and that happens throughout, who knows, 6, 10 hours, 2 hours, 3 hours. It's not consistent. So in this problem, we're accounting for that. All we're saying is like in the first hour we got a rainfall excess or runoff volume of 0.2 inches. In the second hour we got a rainfall excess of 1 inch. In the third hour a rainfall excess of 0.5. So we have three different hydrographs where their volume underneath their curves are 0.2, 1 inch, and 0.5. So given these three values and given the template of that storm, or in other words, the unit hydrograph, we can develop a composite runoff hydrograph, a hydrograph that represents that storm, even though it had different rainfalls at different hours. So the way to do that are three methods: the convolution equation, matrix multiplication, and table methods. The convolution equation and the table methods are pretty much the same. So when I solve them, you're going to notice that they're very, very similar. I feel, this is how I understand it. I feel like convolution equation is mostly when you are doing it on a paper, like handwriting it, solve it on your own on a paper. And the table methods is the same, but using Excel or a similar software. The matrix multiplication involves matrices, so that's different. But let's start with the convolution how do you spell that? Convolution method. And the way you do that is all we need to find out now are the Q values. So we're gonna make a list of, we have 1, 2, 3, 4, 5, 6, 7 Q values for the unit hydrograph. So let's make a list of this Q2 equals, let's start with the 7, Q3, Q4, Q5, Q5, ah, Q5, caramba, Q5, Q6, Q7, Q8. Oh, let's go for Q7 so far because we have 7 values here. So all you need to do now is follow this process. You need to multiply each of the rainfalls by each Q value of the unit hydrograph. And you're gonna do it this way. Equals this F4, so we absolute that cell, times the first value of the runoff, the unit hydrograph. When we have that, you just drag it down. So you got this value multiplied by each one of this in the unit hydrograph. Now you do the second rainfall volume, which is going to be equal to 1 times all of this, which is going to end up being just the same values as the runoff, as the unit hydrograph, times, oh, just the first one, and then drag it down. And the last one is going to be same approach. Let's F4 that times the first, and then dragging down. So this will be Q8 and Q9. And then all you need to do is sum them up. Let's do equals to sum of Q1 will be the sum of all three. This will be zeros. So that will give you 0, and then just drag it down. Now I'm going to explain what we just did. Why do we skip 1? We skip 1 because this rainfall excess happened during the first hour, and this one happened during the second hour. So this didn't start as until 1 hour after the storm started. And this one didn't start until 2 hours later the storm started. So Q1 represents as soon as the storm starts, we have 0 rainfall excess. And that's why we get 0, and there is 0 in this one and 0 in this one as well. So we wait 1 hour to start our next storm, and we wait another hour to start this one. If this were here, let's say 3, 1, 3, and 6, you will have to multiply this the same way we did this. But then this, since this is 3, which means it didn't start until the third hour, you need to wait. In their case, it would be, you have to wait 3 hours, so you wouldn't start until here. So here you start putting 1 times the first value, and you go all the way down, probably here. And the same way, if this is 6, you gotta wait. It didn't start until the 6th hour. So 1, 2, 3, 4, 5, 6, you will start some in here. And then you will do it all the way down, which you will make you have more Qs, Q10, Q11, Q12 probably. And then you sum them up, and then you get the convolution method for a composite runoff hydrograph. Now, the nice thing of this convolution method is that when you plot it, you can get, let's see, let's use here, this is 0, 1, 2, this is the, let's use it as the hours, 6, 7, 8. So these are the hours of the total storm. So when we plot them, let's grab all this data, insert chart. We don't want the chart, we want this. And let's get rid of, remove all series, data range, horizontally at x-axis, and we want to use the column A, 16 to 25, and then the series, let's use this one first, which is F, column F, which week happened? I don't see it. This is annoying. Why is that not working? I do not like spreadsheets. F here, finally. Oh, x-axis A, this is F. Okay, now it's working. Um, so this is the total composite. But the nice cool thing of this method is you can also plot each individually and see when they start if you follow that approach. Now let's do column C here, which will be the first storm of 0.2 rainfall excess. Column C is right here. No, wrong one. A here. Add series, column C. What is happening? This is the total. Add series, column C. Okay. Now we have at the very first, the zero point 0.2 inches rainfall excess multiplied by the unit hydrograph. Now, if we add the other one, C, D, and E, we see each one of them individually. And this started at time 0. The 1 inch rainfall excess multiplied by the unit hydrograph starts 1 hour later. And the third one starts an hour after that. So, and these are their approximate shapes of each one of them. But what we do with this is we find one hydrograph that represents all three of them, which is the blue line in this plot. So this is, and again, this is time versus CFS, which is the flow. So this is a nice, cool way to approach this. So gives you a good visualization of what's happening. Now we have another method that is the matrix method, matrix multiplication method, right? Let's do that, multiplication method. And all this is doing is we are getting Q by multiplying the unit hydrograph times the rainfall excess. It gives us Q. That's all we're doing. That's also all we did here. The rainfall excess times the unit hydrograph gives us a Q values. But here we're gonna use them as matrices. So we need the unit hydrograph as a matrix. And if you remember from your linear algebra, to multiply matrices, we need to make sure that the first matrix has the same amount of columns as rows of the next matrix. So the unit hydrograph needs to have, let's say we have the rainfall excess. So we have the unit, sorry, this is rainfall times unit hydrograph. Let's do it that way. So we have that the unit hydrograph has 1, 2, 1, 2, 3, 4, 5, 6, 7, 7 values here. So we need to make a matrix of 7 columns with the rainfall excess value. So this is how you do it. You use the three values 0 0.2, 1, 0 0.5. And all you do is copy them and skip a cell vertically. Control C, Control V. And you're gonna do that 7 times, 3, 4, 5, 6, 7, and then fill everything else with zeros. I don't know if Excel already take them as zeros once you multiply the matrices, but let's just do it also for purpose of visualization. Okay, we're almost there. Okay, so we have the rainfall excess matrix. Let's do bars at the end so we can visualize it better. And now we need to multiply that by the unit hydrograph, which in our case, our runoff of the unit hydrograph are these values here. We copy and paste values only. And again, let's, oh, all of it, left and right. Okay. And if we multiply this, equals, can do that, equals, now it says equals, it's gonna give us all we need to do is multiply those matrices. So the formula is matrix multiplication and MULT, and we grab the first matrix, comma, the second matrix, and we get these values. And if you notice, these values are exactly the same as the ones that we found on the convolution method. The only difference with this method is that you can just plot the final hydrograph. It's much harder to plot each individual hydrograph as we did here on this method. And honestly, this is it for matrix multiplication. It's just mostly the setup. Then the rest is done by Excel. And the table method is exactly the same as the convolution, except that you just do it here. Oh, I wanted to show, let's say, convolution method, pretty much you do the same. I won't spend time doing that, but you do the same. Just it's just mainly to do it like when you are writing it on a paper, like doing it on your own. Handwriting the whole process and adding up on your own. And the table method is the same. You just need to multiply this. Let's do times O and 4 times each one of these values. I'm gonna do it. You can totally skip this part. I just want to show it's exactly the same thing. So we have this. Okay, so let's just drag this down. 7 times 4, 5, 6, 7. And then we do the next one, which is equals to this F4 times the first value, and then drag it 7 times. And then the next one equals to the last rainfall excess value, F4 times this, and then drag it 7 times, and then add him up these three values. And if you drag this, oh, that doesn't look right. Something happened. 0.5. On this case, I think you need to 0. Let me check. Oh, I didn't. Okay, so this is what happened. This should be 0. I should have started 1 down. So this is equals to this F4 times the first value, and then drag it 7 times. There we go. So I think I didn't skip 1 cell down. So, and you notice all these three are exactly the same. You get the same, you should get the same values. With those are just three different approaches to perform a composite runoff hydrograph. Um, so this is the way how you work with hydrographs and unit hydrographs. Hopefully the concept of a unit hydrograph makes more sense to you. Now it's just a relationship of the runoff flow values of a normal hydrograph with, but in our case for a unit hydrograph, instead of a precipitation of 5.87, for example, sorry, not precipitation, a runoff volume of 5.87 inches, we just divide all those flows by 5.87, so we can get 1 inch as the volume underneath the curve. So that's it conceptually. Hopefully these exercises help you at least to understand a little better these new concepts. In the next video, I'll be solving I will say an extra bonus problem, a special problem of hydrographs and unit hydrographs. So see you then. Good luck solving these problems. Bye.